All right. Here we are again. Okie dokie. I'm actually quite excited because we are about to finish the videos for the series Introduction to Parametric Modeling. Oh, sorry. I'm grabbing a snack. I haven't eaten in a long time. So, what am I going to do? We're going to record. Actually, this one doesn't need. Sorry, I'm just stuffing food up my mouth. Can you still hear me? Yeah. Sorry, I'm stuffing food up my mouth. Give me 1 second. So I'm going to first let me save this, and then let me close it, and then what we're going to do is we are going to. Okay. So what are we doing this afternoon again? Like we're streaming 3 times today. So I am going to do the 2 exercises that I'm missing that I want to wrap up for images, and therefore images, and then and then after that we're going to be done. And then what I will do is offline I will prepare a small presentation, because tomorrow I want to record a video saying something like I want to record an introductory video like, hey, this is Introduction to Parametric Modeling. You're going to learn how to see this and that and blah 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 and so and the other. And for that I would kind of like to have a video with small clips of interesting things that we did over the course of the playlist. So that is going to take me a little bit of time to prepare. Maybe I can do it tomorrow during the stream. That could be interesting, perhaps. Maybe. Maybe not. I don't know. Maybe not. I don't know. And maybe what we can do tomorrow is, yeah, we can. What we can do is we can use that to do some Camtasia kind of situation. I'm having an idea here, actually. And let me write that down. Intro video. Do it during the stream. Show Camtasia workflow. So Camtasia workflow, clip videos, make a PPTX with them, record the video. I think that could be cool. That could be super interesting, actually. All right. Okay, so but in the meantime, this afternoon, what are we do? We are going to record the 2 videos that we have left, which is creating a pattern from an image. So that's going to be one thing. And the other one is going to be recreating a topography from an image. Okay, so how are we going to do that? I have the examples that I want to use here. Exactly. So, okay. All right, so For this one, I'm not even going to draw anything on the whiteboard because it's just going to be that easy. So so okay. I'm going to throw here. I'm going to throw here. Oh, okay. All right. So let me put a slider here, and this is going to be grid size. Okay. So that's going to be 10, for example, and then another. So that's going to be number. We're going to call this number of cells, and therefore okay. All right, and this is going to be, what is this going to be? E28 is going to be E28 image image God image based pattern. And then what we're going to do is I will record the introduction later, but I'm going to start right away. Okay. This exercise is going to be so easy that I'm not even going to do any sketching on the whiteboard. And you already saw in the introduction what the exercise is going to look like. So I'm just going to cut to the chase and start writing code. So what I'm going to do is I have a couple of sliders here that I will use. And then I just dropped an image sampler from parameters, input image sampler. I just dropped one here, which I'm going to extend to make a little bigger. And then what I'm going to do is I'm going to double click and I'm going to load an image that I have here from myself. Okay. Then because in the previous exercise, in the previous video, we saw how by default the domain of the image is from 0 to 1. This I can change, so I can make it, for example, from 1 to 10, so that the image, in a sense, is a little bigger here on the Rhino viewport, if you will. Okay, and then what I can do as well is that I can choose from here. I can choose what is it that I want to output from the image sampler. So right now we have RGB colors, but I think because I'm going to create patterns of circles that open bigger or smaller, I'm not going to use the RGB colors. I'm just going to use the intensity. So how bright a particular pixel is going to be. And this will be a value of from 0 to 1, with 1 being super bright and 0 being not so bright. Okay. You see that the image sampler turns black and white because that's a more accurate representation of brightness. Okay. And I'm going to plug in here a panel to get a sense of what's going on. Now, what I would like to do is I would like to create a grid of points that I'm going to use to sample this image. So what I need to do is I need to create a grid of points that go from 0, 0 to 10, 10 at however much intervals. And this is because the grid of points are going to be here physically in Rhino, but also it's important that those points have the same coordinate space than the image. So what I'm going to do is I'm going to create a grid of points that is going to be square, and then how many, the base plane is going to be fine, the size of the grid cell. So how many grids, how many points, how many elements are on each direction will depend on my number of cells. So for example, I'm going to do 10. And then the size of each cell will be equal to the size of the whole thing, which we agreed was going to be 10 units, divided by how many cells I have in each direction. So that's why I need to do a division where I'm going to divide the total size of the grid by the amount of elements, and that will give me the size of each one of the grid cells. And therefore, if I have more cells, then they are smaller, but if I have less cells, they are bigger. Okay? Right, okay, so now I have here a collection of points. Those points have coordinates in world coordinates, 0, 1, whatever, blah, blah, blah. But I don't care about world coordinates. I care about the domain space of those points is going to be similar to the one in the image. So what that means is that from 0 to 10, my image is also sampled from 0 to 10. And therefore, now each one of those points has a value for the brightness. So you can see that some points have low brightness and other points have high brightness, etc., etc. And what I can do now is I can use those values to drive the dimension of a particular element. So for example, I'm going to turn this off, and I can use those to drive the dimension of particular elements, for example, a circle. And if I drop a circle here and I choose all these vertices as the centers, and if I choose all these radii as the diameters, you can see that something is happening. So I can see that more or less there is like a sense of larger circles around and smaller circles here. And if I crank this up, it looks like there is some kind of pattern arising here that looks like the image. So that is great, but you can see that because I'm using just the straight numbers 0 to 1 as the radii, then this is not working entirely. It's not working entirely because the circles should be smaller the more cells we have. So what we need to do is we need to multiply this 0 and 1 by the size of the cell so that the circle adapts to smaller cells or bigger cells. So I'm going to add here an expression, and this is going to be cell size, and this is going to be brightness, and then the cell size is going to be here, and then the brightness is going to be this one, and then I'm just going to multiply here the cell size multiplied by the brightness. And as I do that, I'm going to plug this in here, and it's starting to work, but you can see that there's overlaps. That's because we are using the radius, not the diameter. So we just need to multiply this by 0.5. And now you can see that, now we're getting something that looks much better. All right. So we get larger circles where the area is brighter, and we get smaller circles where the area is dimmer, which could be a way to go as the pattern. And let me actually crank this up so that we have like more definition. So this is starting to look pretty cool actually. But I would argue that perhaps, and even if we do like a planar surface, like a boundary surface, it's going to look even better. So it's going to look something like this, right? However, I would argue that I kind of want the opposite effect. I kind of want less or smaller circles where things are brighter, and I want bigger ones where the element is bigger. So I think what I would like to do here is I would like to say that perhaps what we want is 1 minus the value of this, or here 1 minus the value of brightness, so that wherever we have a lot of brightness, the value is very small, and wherever we have tiny brightness, the value is bigger. And then I can do that, and you can see that now this is starting to look a little better. Hold on. Is this looking good? And it's starting to look a little better. By the way, I never gave credit. This image was taken by my friend Nono Martinez Alonso. So it's always good to give credit. And something that I also want to try is if I can find I can implement something where under a certain radius, under a certain size of pixels, we're just not going to take that into consideration. So what I would like to do is, if certain circles are smaller than a particular value, then just remove them completely from the list. So what I can do is, I'm going to say, here I have all the values that I have computed, correct? Or maybe I'm going to work directly here with the brightness, okay? So I'm going to take all the values for the brightness, and I'm going to check if the value of the brightness is over a particular threshold, or AKA, if the value is very, very bright. So how do I do that? I can go to mathematical operators, and I can use, for example, a comparison operator that is called larger than. With larger than, what I can do is I can compare if these values that are coming here are larger than a particular value. So for example, 0.9. And if I do that, then I can what the result of this is going to be, what the result of this is going to be is a list of true and false values that tell me whether if a particular number is greater or not than a particular one. And with this list, what I will be able to do is I will be able to remove from this data tree any element that is false and keep any element that is true. So for example, I'm going to use call pattern, and we have seen this one before, I think, where we take a list and we take the pattern used for calling, so a list of true and false values, and then the component removes those values from the list. So I'm going to take this list, the list of values, correct? I'm going to take that and I'm going to apply this pattern. And you can see that now the comparison is that what I have is only the values that are greater than this value. So I actually want the opposite effect. I want the ones that are smaller. So I'm going to repeat this, but with the other. So I'm going to repeat this, and I'm going to repeat this. And now what I have kept is only the values that are smaller than a particular value. And then as I plug this in here, you can see that, oh no, what happened? We're having data problems here. All right. So what that means is that I need to call not just the numbers, but I also need to call the points that I'm using as the baselines for the circles. And that is going to be something like that here. And now you can see that the more I lift the limit, the more circles we get, but the least, exactly. And then if I go all the way up, then I get all the circles. But if I go to, for example, 0.8, like a lot of these bright values are starting to leave. You see? And I could also create an animation with this, actually. But I'm going to leave that up to the user. So in case I didn't explain correctly, so the problem that I was having was that I was trying to put circles on, I was trying to create circles with all the points on the grid, but I was giving it less values of brightness because I had called the values of the brightness. So what I can do is I have to take the list of points, I have to call it also to remove the points from the list that have a small brightness, and then just draw here on the circle the ones that have the large brightness. Okay? All right, and I think that's it. That's all I wanted to do for this exercise. Now I can bake this, for example. I can use it at surfaces, and then I can now, I don't know, this is a shaded thing. I could use those circles for laser cutting. I could etch something. I could just put my face in the back of my laptop with a laser cutter. I don't know. There's a lot of things I could do. You could do with this kind of patterns right now. Okay. All right. So with that, I think we have completed the exercise. What was it? Like 7 components? This was really easy, actually, and very nice to work with. Wonderful. If you make some version of yourself using the technique, please share your work on the comments and or on our Discord server. We will be very happy to see it. We will be very happy to see it and to broadcast it. Okay. Thank you very much. If you like the video, maybe click on the like button, subscribe to the channel, all those things. And in the meantime, thank you very much and see you on the next video. Bye bye. Okay, and now I'm going to record the introduction to this video. Okay, we're going to put this here. Hi, this is Jose Luis here, and welcome to a new video on this series, Introduction to Parametric Modeling. In this one, I would like to make a super simple exercise where we're going to take an image and we're going to use the brightness of the pixels on that image as the values that are going to drive the diameter of all these circles, so that we will be able to generate kind of a representation of my face using circles that are bigger or smaller. And of course, everything is going to be parametric, so we're going to be able to increase the resolution of how many circles we're using to represent this image, so that it starts looking a little more defined, right? And I will show you as well a technique to use conditional statements inside of Grasshopper to add or remove elements. So in this case, for example, I'm going to implement a kind of cutoff where we're going to be looking at a level of the brightness, and I'm going to be removing circles for those pixels that are under that value of the brightness. This is going to be a super simple exercise. It's going to take us like 6 components to do, and it's going to be super nice because it could generate a pattern of circles that you could use, for example, for laser cutting or for etching or for creating stickers, or I don't know. That is absolutely up to you. Okay? But it's going to be super simple and super straightforward to do. Let's get done. And also, I mean, even if you don't want to learn how to do this, you can just take this file, replace your image there, and then just be done with it. You know, it's as simple as that. So let's get hands-on and let's get started. You're right, Said. Or robot printing. Absolutely. That also works. That also works very well. Okay, so that was it. That was one. And then the other one that we want to do is going to be topography from an image. This one is going to be very, very cool. So that's going to be this one. I'm going to save this and I'm going to remove this one. Okay, I'm going to be done with that. Mm-hmm. Okay. All right. So the next exercise we're going to do is going to be we're going to take an image. We're going to sample that image with a lot of points, and then we're going to move those points in 3D, and we're going to create a nerve surface or a nerve surface or a mesh with each one of them. Okay, and we're going to do both, and I will explain what advantages each one of them has. So, how am I going to do this? It's going to be super easy, actually. So we're going to start with an image. Why am I drawing that so high? Actually, wait, I actually did like that one a lot. So, why can't we just... We're going to start with an image like this, exactly. And then this is going to have an image like whatever. It's going to... And I mean, it's going to have whatever the image, blah, blah, blah. It's going to be whatever the shades, right? Whatever the shades is. And then what we're going to do now is we're just going to place a bunch of points on it. We're going to place a series of points on it. Then for each one of those points, we're going to calculate the RGB values. Here, we're going to calculate the RGB values. And then we're going to use, no, sorry, not the RGB values. We're going to calculate the brightness. Which is going to go from 0 to 1. And then we're going to use that to move the points. Oops. We're going to use that to move the points up. a controlled amount. And then once we have that, we are going to create a new mesh. Oops, not that one. And then this. That mesh is going to be I don't need that. I don't need that. And then once after we have that, what we will do is we will do the typical thing where we create a vertical set of planes. Create a I can explain that. So we can do that. And then we will want it doesn't look terrible, right? Okay. All right, so let's do this. This exercise is going to be super simple and super easy as well, because it's going to be just basically mixing everything that we know how to do at this point. So we're going to start imagining that we have an image, and that image has some kind of grayscale tones to it that represent how high a particular terrain is. And then given that, it's going to be as simple as we have done in the previous exercises, where we're going to basically sample that image with a grid of points. For each one of those points, we're going to fetch the brightness of the image as a value that is inside of the range from 0 to 1, so 1 being very bright and 0 being not so bright. And then we're going to take all those points and we're going to move them in a C-space at a value that is going to be a factor of that brightness. So I don't know, 5 times the brightness, 10 times the brightness, however much the scale of the terrain we want that to be. That will give us a cloud of points that are now somehow in 3D space. And then if we join those, if we reconstruct them with a mesh, we will get a mesh in 3 dimensions, with each one of the points representing the height of the terrain. At a secondary, after that, we will just do a very simple operation like we have done before. We will generate a set of parallel planes in C, and then we will cut the surface, we'll cut the mesh with those planes in order to create the contour lines of this terrain or of this landscape. And maybe, I don't know yet, but maybe after that, because these contour lines are going to be in 3D space, they're going to have different heights. Maybe something that we could do is we could project them all together to the XY plane in case we need to print them as a map or something like that. One thing that I would like to do is I would like to do this exercise reconstructing a mesh, but I would also like to make this exercise reconstructing a NURBS surface instead. And I would like to do that because you will see that the quality of how the contour lines are going to come up is going to be very different, but also the performance of the algorithm is going to be very different. So depending on what do we want to do with those ISO curves, then we will choose one method or the other. But I'm going to provide both options for you to choose and for you to learn more as well. So let's get hands-on. Let's go back to Grasshopper. All right. Okay. Okay, so I'm going to have that. Oh, image sampler. Okay. Yeah, I don't need a Rhino file for that. Okay, let's get started then. The first thing we're going to do is I'm going to load the image that I want to bring in. So I'm going to go to parameters, input, and I'm going to drop my image sampler here. And then I'm going to double click on the image sampler and I'm going to find in my computer this file that I have that is called the height field from TerraGen. This is a file that I downloaded from Wikipedia. Let me hold on. Let me find that. Yes, exactly. If you Google height map Wikipedia, it's literally the first image that shows up here that was generated with a computer, so with TerraGen, which is a software for generating terrains, which is actually really, really nice. I've used it in the past. Anyway, so I'm going to use that and I'm going to maintain that the domains are I'm going to scale the domain up a little bit from 0 to 10 so that the image is a little larger here on the Rhino space. Then what I would like to do is, as I have done before, I need to generate a grid of points to sample the image. Now, for the reasons that I'm going to explain very soon, in this case, I am not going to generate that grid of images by creating a square grid like I have done in previous examples. But what I'm going to do is I'm actually going to create a flat planar mesh that is going to have all these a control amount of squares in the U and V direction, and it will be that mesh that I will deconstruct to obtain the vertices that I will use for sampling. So I'm going to go to meshes and I'm going to primitives and I'm going to go for mesh plane. As I do mesh plane, you can see that the boundary is going to be the rectangle that describes the boundary of this surface. For that, I will need to create an actual rectangle. So let me create a rectangle which is going to be centered on xy, and then x is going to be 10 units, and then y is going to be another 10 units. This takes a domain, but I'm just going to give it one number, and I'm going to get a rectangle that is this big, and I'm going to use that rectangle for the boundary. Then how many faces along the x and how many faces along the y is going to be defined by this other parameter here that I have, and it's going to be the same in both directions because the image is a square. Okay, so with that, what I have created is a mesh that contains all these vertices and all these faces, which is great. And then that is a very, and if I deconstruct such a mesh, then what I will get will be a grid of vertices that are going to be equally spaced. So in a way, it's a very similar process to what I did in previous examples with the grid. It's just that we're going to start with the mesh instead. This will have advantages that you will see very soon. Now, I have created my mesh, and then I am ready to sample each one of the vertices, to sample it with the image. What you can see is that the image is giving me RGB colors because I forgot to tell the image sampler that I only want the brightness. So I'm going to click on the brightness, and now I get values from 0 to 1. And then, in order to now recreate the mesh, all the points that I had below, what I'm going to do is I'm just going to move them up in the Z direction, an amount that is directly proportional to how bright those pixels are. We know that from the data. So the only thing that I need to do is, for example, let's say that I created directly a Z vector with these values, right? So if I do that, then I can now move all those vertices in Z that contain amount. And you can see that I already start getting an effect of like some points are going higher, some points are going not so high, all right? Which is it's starting to be pretty nice. I'm going to leave the mesh there actually. And then what I would like to do now is with these points that are above the mesh and that have been modified by the height field or the height map, what I would like to do is I would like to create a new mesh that has its vertices moved in 3D space like with this logic. So the only thing that I need to do is I need to go to primitives and need to click on construct mesh. Construct mesh is going to require all the raw information that a mesh needs to be created, which is going to be a list of vertices. Those will be the vertices that I just created new, and a list of faces. And this, having a list of faces, needing a list of faces, is the exact reason why I chose to create the grid of points, in this case, from a mesh. Because since I created a flat mesh that already had the information for the connectivity of the faces, so it already had like all the quad faces and all the indices, this information would have been pretty difficult to recreate in order to make this mesh now. So because I already have it here, and because the topology, so the same points are going to be joined with the same points. It's just that I have moved them in the Z height, but they are going to be connected with the same quads. So that's why I can reuse this information. Is going to come in very handy now to just plug in here directly. And if I turn out the base plane, you can see that, very nicely, I have this mesh now that is resembling this topography. Is that so? Let me crank up this. I'm going to do 50 and I'm going to turn off the points. And is this topography kind of looking like this? It looks like this area is more depressed. This area is more like a ridge here, right? It looks like there's like some mountains here, which kind of fits this. And this area is also higher. So this area is also higher here. So Ta-da! This looks like it's working. And if I bake it, and I do, for example, like an eyes, what is it, like a render kind of view of this. Oops, sorry. You can see that this, you can already see how this mesh is kind of looking like this one here. So that's great. So what was that? 5 components that we used to generate a mesh with volume out of an image. I think that's pretty badass, if you ask me. Not because I did it, but just because, you know, I think it's actually, I actually think it's pretty cool. Paramodel Professor Meister. All right. So what else are we doing now? I want to factor the height, and I also want to give color to the mesh. One detail we skipped through, we tiptoed over, was the fact that I have used the values of the brightness here right away straight, and therefore the maximum height of each one of these points is going to be 1. And maybe that's not what I want, because maybe I know how much a pure white value for this particular image is, for example, like 3,000 meters. If it's, I don't know, if it's a mountain, whatever. So what I would like to do is I would like to factor this height by a value, so that, for example, if I know that the pixel with maximum brightness is 3,000 meters, then I can set here 3,000 meters, and then that will basically scale the whole terrain accordingly. So that's just going to be a simple multiplication operation, taking each one of these values and multiplying it by a factor, and then using that as the C value. With this, now I have a way to control the overall proportion of either absolutely flat, or it starts growing into like a serious topography with serious mountains, right? So maybe we like something more like this. I don't know. That's one thing. The other thing is, we are using meshes, and we also know that meshes give us the opportunity to color them, because they give us the opportunity to add vertex colors to each one of their vertices. So since we have the mesh, why not use this image also as a texture that we're going to apply to the image? So what I can do is, here, when I construct the mesh, remember that I can plug in vertex colors. So what I can do is I can use the exact same image sampler, but I can copy and paste it. But now, instead of using the brightness value, I'm going to double click here, and I'm going to take the RGB colors. Sorry, I pressed cancel. We're going to use the RGB colors so that I have a full RGB spectrum here. Because imagine, if I plug this here right away, what I'm going to get is, well, I'm going to get errors, that's for sure. So that's why I would like to take, instead, I would like to take full colors. So that's why I need to do another sampling operation. And if I plug this in here now, you can see that my mesh now actually does have the ridges and the valleys. They have them colored specifically for according to its height. So I'm going to bake this now, and as I do, I got my mesh there, and you can see that the higher points are white and the lower ones are black, which is also kind of cool, right? And you can imagine like a fly through here. You know, how cool is this, huh? All right. Okay, and the last thing that I would like to do with this mesh is we probably want to now do something where we slice this mesh with a lot of parallel planes in order to get the iso curves that define the height of these meshes, okay? And in a very similar way as we have in maps. So let's take a look at how we could do that. As we have seen before, we could use the method of the bounding box and the planes, whatever, but I'm just going to keep it simple. So I'm just going to create a simple XY plane that is going to start at 0. I'm going to add a couple parameters. So for example, a value that is going to be, for example, iso curve height. So how many, what is the distance between isocurves? And I'm going to set this to a value, a fairly small value, 0.1. And for example, another one that is going to be number of isocurves. And that's going to be, for example, 100. With this, what I'm going to do is I'm going to copy this plane 100 times, or however many times, at a distance that is controlled by this height. So I'm going to create a series of numbers that is going to start at 0, that is going to have, the step size is going to be how far away they are, the isocurves, and the amount of values is going to be how many isocurves do I have. That is going to give me a series of numbers that is going to look something like that. And if I now use that to create C vectors, I'm going to create all these C vectors, and I can use those to move the original XY plane, hence creating a collection of planes in 3D space, which I can obviously now take and use as the cutting planes for this mesh. So I'm going to take all these planes, I'm going to move all this logic somewhere, I don't know, I'm going to move it somewhere here, for example, and then I'm going to take this mesh and I'm going to section this mesh by all these planes. This is going to be very similar to what we did in the previous exercise when we did the slicing. So I'm going to go to intersection, mathematical, and I'm going to use mesh versus plane. I'm going to take this mesh and I'm going to cut it by all these planes here. And whoa, nice. Look, check that out. Let me hide the planes, but check that out. How cool is that, right? So we have now my image from the previous exercise. We have now the terrain, which is a mesh. We have now the terrain has been colored, and we have like all the isocurves, which pretty much look like a plane, like a map, right? And if I actually turn off the preview mesh edges, so now you can see how we have kind of grouped similar colors with these cutting planes, and then you see that all this black area, and this white tips here, and I'm going to, and this is looking really, really cool actually. And of course, this is parametric, so I'm just going to move this to my other screen, and I can add less height between the curves. I can have more curves, etc. But I can do, for example, 0.05, and this is going to look very, very nice. Okay. All right. This is great. Now it's looking pretty good. Now, what do we want to do now? The last thing that I would like to do is I would like to take all of this and I would like to project them to the XY plane so that in case we need to laser cut them or in case we need to plot them or print them, they are all on the same plane and it makes things a little easier. We could also color them by height, actually. That could be interesting to do. But anyway, let's do that first. So what I'm going to do is I'm going to take I'm going to go back and dock my grasshopper here, and I'm going to take all the curves, and what I'm going to do is I'm just going to project them onto a plane. So I'm going to take all this geometry and I'm going to project that geometry to an XY plane. And if you see, and if I hide that, and if I hide that, you can see that I have now created this projection that is planar, but it's on the XY plane and would allow me to print and to do whatever I want with this. Can you see? All right, so this is great. It's looking great. However, however what? However what? What do I want to do now? What do I want to do with this now? Oh, I wanted to say that the projection is part of the transformations. So I want to say that now. I want to say that now it's a transformation. And then what I want to do is I want to, yes. Yeah, okay. Yes, so I forgot to mention that this projection operation that just came out of the blue is actually part of the transformation. So it's not only Euclidean transformations or moving, rotating, but projecting things is also one of the transformations that we can do because they actually move them in space and sometimes they scale them, etc. So it's also part of the operations that we can do. And the last thing that I would like to do is I would like to highlight one property of this. So if you look at the isocurves that I have generated, turns out that they're not very nice because they're coming from a process that has suffered a lot of discretizations. So for example, a pixel image is already a discretization of reality. Meshes are also a discretization of reality because you take reality and you chop it in phases. And because phases are planar, turns out that we get a lot of situations where the curves, well, basically the curves are polygons. That's one thing to notice. The other one is that in many instances we have several situations where we have a lot of perfectly parallel lines because we have cut the same triangle by multiple planes. And we have these very abrupt kink corners, which they're not very nice. And look at this. If I zoom out, you can see how these patterns, these moire patterns, are arising because of these parallel faces. It's just not a very nice thing. So I may want, if I can, I may want to, for example, smooth out these curves. I may want to create curves that are actually curved and that they transition smoothly between all these planes, all these points of the polyline, so that the curves look a bit more natural because terrain is not just triangles in 3D space. Terrain is typically like made out of curves. So how could we smooth these isocurves in a way that it makes them feel a bit more natural? I see two ways around this. One could be the quick and dirty, which is taking these polygons and then basically for each one of these polygons creating a curve that is interpolated on each one of the vertices that forms that polygon. So if I have a polygon, if I have 4 points and I trace an interpolated curve between them, then I may end up with something that is a bit more natural. That's actually fairly easy to do. Here, if we do, for example, if I take all, if I take all the polylines that I have projected, and I can do this on the projected ones, or I can do them on the ones in 3D space. It doesn't matter. But I can take the polygons that I have projected to the floor, and then I can, for example, I can take this and I can explode each one of the polygons to obtain the vertices. So I'm going to take this, I'm going to explode them, and I'm going to obtain all the vertices for each one of the sections, for each one of the polylines. And as I do that, what I can do now is take each one of those lists of vertices, which are very conveniently organized in branches, and then I can just pass that by an interpolated curve, and the result will be something like this. So if I stop sharing, you can see that now the things, so if I overlap, you can see how from this polygon, now I have this kind of curve going on, and from this polygon I have this curve here as well. So it looks like, and from here I'm also getting this result, so it looks like it's kind of doing its job. So it's working pretty well. However, the problem with this approach is, well, it's not very exact, but honestly, given the whole process that we have followed, I don't think that any process will be very exact. But my main concern is that in areas where there's a lot of density of polygons, then these things are going to happen. What's going to happen is that because we have so much density, then some of the curves are going to overlap with each other. So for example, this is happening here because they are so close to each other, and this line is so big that the interpolation algorithm tries to smooth out, and it actually overlaps on top of the next one. This, to me, it's actually a big problem because this is very strictly wrong. If you're doing a map that has isocurves that represent differences in height, then having these curves overlapped is a tremendous mistake because it just cannot happen physically. So I'm going to propose an alternative method, which is the cleaner parametric method, which is that instead of relying, so for example, you see it's happening here and here as well, and here, is it happening? Yes, here, for example, we have another overlap. So I'm going to propose the following. I'm going to propose that instead of creating curves that are coming from the polygons that we generate from cutting the mesh, what I suggest is that instead of that process, which is kind of dirty, why don't we just, instead of creating a mesh in 3D space, instead of creating a mesh in 3D space, which is very nice for representation, etc., but for the sectioning, instead what we can create is an actual NURBS surface that already embeds and it's already infinitely smooth. And then it is that smooth surface that we create from the terrain that we section with the planes, and it's already going to give us smooth curves for this process. So how would we do that? Well, let's go back a few steps and go back to where we created the planar mesh that we then decompose into all these points. And then when we create another family of points that were the points that define the topography of the terrain. Then at this point, what we did was we reconstructed a mesh so that we could have some kind of geometry to see that form, and also because it was very nice to have the colors projected on the mesh. Don't get me wrong, that's actually pretty cool. But with these points, there are actually ways that we can use these points to recreate an actual NURBS surface. And this is because it turns out that these points actually do have, as opposed to meshes that come from example from 3D scanning, from other processes that are more involved with nature. But if you look at this, these points, even the modified ones, they have a fairly clean and cut logic, which is that they are laid out in XY with a particular direction of U and V. So it turns out that there are ways of reconstructing surfaces from a cloud of UV points that are nicely laid out in 2 dimensions like these ones, and then create a nerve surface out of that. The way we can do that is if we go to surfaces and if we go to, where is that? To freeform, you can actually see that I can create a surface. One of the options is to create a surface from a grid of points. So I'm going to place this here and let's take a look at what the component is asking me. It asks me for the grid of points and it asks me for the number of points in the U directions and the and whether if I want to interpolate samples or not. So I'm going to give the points here and you can see that all the points are on the same list because of the double wire, but also if I look here, there are no branches, everything is on the same list. So that's a good thing. And then U is going to be the number of points in the U direction. We know that we divided the mesh in this many U points. So I'm going to plug this in here and it did not work. It did not work because I did a tiny mistake, which is the fact that we need to read the fine print always, okay? The fine print is that U is telling me is asking me for the number of points in the U direction. Whereas what I have done here is that 50, I have used it to define the number of faces in the X direction. And as we have seen in previous exercises, when I divide something in 3, 4, 5 spans, what I end up getting is 4, 5, or 6 points, or 1 more point than the amount of divisions. So what I need to do is just a simple rule here, where I'm going to add to this, I'm going to take this off, I'm going to add here the number 1, and then boom. And as I do that, you can see that now I have this thing that looks like, let me bake this to make sure that it's a surface. I'm going to bake this and I'm going to move it all the way here. And you can see that, what? It's actually a real NURBS surface. It's not an actual, and if I click on it, it kind of looks like a mesh, but you can see that it's not triangles, that each one of the edges is actually a tiny curve. So these are basically the ISO curves of the surface, but they are not really faces. So this is an actual NURBS surface, albeit one with a lot of definition and where the polynomial is probably crazy to figure out, right? But yes, so that works. And if I actually click F10, you can see how many control points this surface has. This surface is probably really heavy in memory right now. Anyway, so what I can do now is I can use this surface that I just created to subdivide it with all these planes that I just created here. So how am I going to do that? So I'm going to section it with a mathematical intersection that is going to be B reps and planes. So I'm going to place that here. The B rep is going to be the surface that I just got, and the planes are going to be, if you remember, all those vertical planes that I created for sectioning. So I'm going to use those. I'm going to plug them in here, and you can see that compare how much more expensive to perform these sections is than doing it with meshes. Meshes and mesh geometry, in a way, it's very computationally lightweight. NURBS operations and intersections are way more complicated, more computationally intense, always. But if we look closely enough, you can see that the intersections are now very nice and very clean, smooth curves. And if I look from the top, you can see that it looks like way more natural than the situation that I had before. And of course, if I now project this to the XY plane, what I will get is this other form of height fields. So all these other isocurves that look way better than what I had before. So I had this, remember, the green is what I had, and the green is what I did from the polyline, and the red is what I just got from the NURBS surface. So you can see like I'm not getting kinks, I'm not getting this weird pointy here, I am not getting the crazy overlaps that I was getting here, I'm not getting, look at the difference in the shape, right? So how much nicer this is than the other. But you see, I'm starting to get errors here because NURBS intersections are not perfect. Sometimes they can be buggy. So you see, I'm missing this area here. I'm missing this part here as well. So yeah. So sometimes NURBS geometry is so complicated that sometimes it's even a little buggy. But I think with this, we are ready now to just send this to printing or send this to, I don't know. Where do we send this? Now, those are the pros. For the case of the isocurves, NURBS surface is a much better approach. For the sake of just perhaps 3D visualization and the coloring of the meshes, perhaps meshes are the way to go. I don't know. I think this is now at this point is up to you. And yeah, and I think that's everything that I wanted to do. So that's what I wanted to do for this exercise. And anything else that I'm forgetting? I don't think so. So if that's the case, then I think we're done with this exercise. This was reconstructing terrains from height maps or height fields. I hope, and we used two techniques, mesh reconstructions and NURBS surface reconstruction. So I hope this was useful, and I hope you now go ahead and take some images from the internet or some maps, whatever, and you try to recreate them in 3D. It's a lot of fun. You could also 3D print this mesh as well, even with the color, and that would be really cool. All right, so that was it. If you thought this was useful and if you like what you saw, maybe consider subscribing to the channel, liking this video, turning on notifications and all those things. And thank you very much. I will see you on the next videos in this series. Bye bye. Oliver, yes, you can of course, you can use the same points and sample many different images and then take whatever results you get from those samplings and then add them together, average them, whatever. It's absolutely fine. You cannot do it on the same component. So you cannot load several images on this one, but you can do one and then another one and then another one and then use different images for each one of these. Perfectly fine. So that's going to be, so let me reorganize all of this stuff a little bit. So that's going to be one thing. That is going to be another thing. This is going to be the generation of the planes. This is going to be the surface, and this is going to be how can I reconstruct the topographical surface from contour lines? That is a pretty good question because it's not a simple one, actually. That is much more difficult to do, which actually could be a super interesting algorithmic modeling challenge. That could be super interesting, actually. I'm going to write this down as a challenge. Ideas for next streams. Reconstruct a topography from ISO curves. Well, it can be done. It's just that it's not straightforward. It takes a little bit of calculations, but it can be done. Especially if you already know the heights of the curves. But now I've written it on my geometry gems, and that's going to be an exercise that is perfectly doable with Grasshopper. Okay? So I got you. I got you. Don't worry. Okay, I need to record the intro video. And what am I going to say on the intro video? I'm going to say that given an image, I would like to reconstruct a mesh that is going to look like that, and where the height and so that's going to be, and then from there I would like to show the sections and project them, Intro 4.3 was awesome. What was 4.3? I forget. What did we do? Roselotus Mystic 4.3. Lines, polylines, and splines. Hi, this is Jose Luis here, and welcome to another video on this series, Introduction to Parametric Modeling. In this video, I would like to make a super fun hands-on exercise, which is going to be how to reconstruct a terrain from an image of a height field. So imagine we have an image which is grayscale and represents how high or how low certain areas of the terrain are. We can actually reconstruct geometry with that volume, for example, by creating meshes or creating nerve surfaces out of that. So for example, here I'm going to start increasing this mesh which I had flattened, but I'm going to start factoring it based on the image map that I have previously loaded into Grasshopper. And then at the same time, something that is going to be super easy to do is going to be to create isocurves, or to create all the curves that are the intersections with horizontal planes, and therefore be able to create like this kind of image that we will be able to project, which is going to be the height field. So the isocurves as if it was a map. Now we're going to do this with meshes because it's very interesting, it looks 3D, but for the isocurves part, the definition of the curves are not going to be great. So for that, I'm actually going to switch to creating this terrain also with a nerve surface, so that when I do the intersection, the curves are much smoother and they look way more natural, because we're not cutting triangles, we're cutting an actual nerve surface. And therefore, when I project that to the XY plane, it looks like a real topographical map, which is going to be super interesting. Okay? It's going to be a fairly simple exercise. It's barely 12 or 15 components, but it's more about the ideas that we're going to explore here that I would like to emphasize. Okay? So this is going to be really cool, especially if you're into landscape or video gaming or those kind of things. So bear with me, and let's first do some sketching and some diagramming to think through how are we going to approach this problem. Let's do this. Yoo-hoo! Whew, whew, whew. I think we're done. We are done. Ah, God, that was a lot. Oh my God. Oh. Mm. Sorry. Okay, so I think I'm done recording content in terms of lectures and exercises for the Intro to Parametric Modeling series. I'm done. That's it. So I do deserve some sleep, Roslotus. Yes, thank you. But so that's going to be it for the list. So what we're going to do is that tomorrow we're going to have we're going to have one live stream in the morning. That's going to be the last this week. And then during that live stream, I'm just going to record two simple videos, which are going to be the introduction video to the whole playlist, and it's going to be the wrap up video to the whole playlist. You know, the video where I say like, hey, if you want to learn more, maybe check out these other videos or look at this playlist and blah blah blah. All those things that, like, how can I keep learning? You know. So that's going to be that. And so, which sounds boring, but in order to do that, what I would like to do is I would like to have some kind of PowerPoint presentation where I run through tiny clips of cool things that we have done over the playlist. So, and in order to do that, I'm actually going to show you a little bit of the workflow that we use for editing the videos, which is a really interesting workflow. We use a video editor to cut things out, but then we use a Python script to stitch them together. So I'm going to show you how we do it and a little bit of the Python code. It's probably the first time that I'm going to be showing Python code in this channel, so it's going to be a milestone here. And then I think that's going to be the end for the series, and then we're going to move on to new stuff in the future. New series, more algorithmic modeling challenges, more geometry jams, everything. Okay. All right, and with that, I'm going to call it a day today. Thank you very much for being there. I'm extremely grateful, as usual, to being in the company of like-minded people who like computational design. Thank you for being there, and see you tomorrow, hopefully at 10 a.m. Eastern Time. All right. Thank you very much. Have a good evening. Bye-bye.